Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will discuss the different modes of heat transfer in cold weather clothing. So, for a clothing we must understand its different heat transfer mechanism to design a proper extreme cold protective clothing. So, heat transfer mechanisms are one of them is heat by conduction. In this process the energy from one medium to another medium is by the direct contact. It is done by the direct contact with each other. So, it actually needs some medium. Rate of conduction can be calculated by this equation, where Q is the heat transfer rate, that is heat per unit time. K is the thermal conductivity of the body, that is of the material. What is the thermal conductivity of any material, like in the present case it is the clothing. A is the area of heat transmission. So, in this case typically our clothing area, and T hot is the temperature of the hot region. In our case it is, in the present case, it is the skin temperature, and T cold is the environmental temperature at the present case. So, if we see that if here with our case in the extreme cold weather clothing, the K is in our control, the thermal conductivity of the material. So, K if we can control, if we can reduce the K value, thermal conductivity we can reduce the value, that means the heat transfer per unit time. So, heat transfer rate will reduce, and also that here D is the thickness of the body. So, if we can have higher thickness, so the Q will reduce. Now, for designing a clothing, so higher thickness will reduce the ergonomic movement of the body. So, we should design a clothing with a lower thermal conductivity. So, thickness increase is there is a limit of increasing thickness. So, we should design a clothing with higher lower thermal conductivity. Then by convection, its convection is the by movement of a fluid from basically from higher temperature region to the lower temperature region. The equation here, this is the equation where Q is the heat transferred per unit time by convection, Hc is the coefficient of convective heat transfer. So, Hc, A is the area of heat transfer, and this is the surface temperature, and T is the fluid temperature. And radiation, this is basically radiative heat transfer through the electromagnetic wave. such as infrared, okay, and does not require a medium to travel. Okay. It can pass through the vacuum, but medium is used to restrict the heat flow by radiation, where medium can reflect the radiative the wave. So, Stephen Boltzmann law, it actually follows thermal radiation. This is the Stephen Boltzmann equation, where Q is the net power radiation, okay, and A is the area of contact, T r is the radiated temperature, T c is the supporting surrounding temperature. So, that is a radiator, our body temperature, suppose this is our body temperature and is a T r or clothing surface temperature, and T c is the environmental temperature, which is at a very low temperature. There we can see here the T c, if the T c is lower than this. So, here T r as T c reduces. So, this value T r power 4 minus T c to the power 4, this value will reduce drastically, and so this value will actually, if T c drops, so this value will increase drastically. So, heat loss will increase, get affected significantly. So, that is we have discussed, typically 65% of the heat loss is through the radiation due to this fourth order equation, and E is the emissivity of the material which is there, and this sigma is the, this is the Stephen Boltzmann constant. Now, we know that these are the conduction, convection, radiation are the thermal transmission mechanism. Now, we should know the what are the thermal insulation mechanism principles. So, creating and maintaining thermal barrier. So, insulation mechanism is basically by trapping air in small space to minimize the conductive and convective heat transfer. Okay. So, insulation effects. So, is this effectiveness is enhanced by air content. So, maximize air entrapment in the fiber structure, okay, which actually reduce the conductive and convective heat loss, and smaller fiber diameter create more air pockets. So, it will create more air pockets with a which are steel air pocket, bulk density, optimum balance between air and fiber arrangement, random orientation prevent air movement. So, random orientation of fibers that prevents the air movement. Okay. So, here you can say poor insulation, if we where the convective heat loss will be high. So, through that through the fabric, if the air moves through, so in that case the convective heat loss will be more, and you can see the effective insulation. So, minimize heat transfer because of the pores are created, or pores are at the inside the structure. So, that it is not open pores. So, the factors which affect the protection protective performance of at the cold environment, these are the different factors. The clothing factors, we can control the clothing, the environmental factors, the body and health related factor and behavior related factors. So, these are the different factors which affect the protection. So, now metabolic heat is the that is the wind chilled, the environment condition, the thermal insulation of the clothing, that is a clothing related condition, air permeability like clothing related condition, moisture vapor transmission. So, that affects the protection. So, moisture vapor transmission should be good, so that it takes away the body fluid out. Now, let us see the air permeability. Air permeability is very important for the extreme heat cold climate clothing. So, if air permeability is high, in that case the through the convection the heat will move out from the body. So, which is basically volume of air passes passing through the fabric per unit area per unit time under certain pressure, that is the air permeability. We can see here with this schematic diagram at different pressure, like high pressure air is passed through the fabric structure, porous material, okay, that is fabric structure, and in through this the air is flowing. So, we can calculate the quantity of air or volume of air flow at what is the air pressure at different pressure level. So, that can be calculated. So, lower air permeability of fabric is required. So, less than 5 CFM is the best, which maximum wind protection and potential moisture build up. So, if we can block all the ports, so wind will not penetrate. So, wind protection will be there, that will be good for the for as far as the wind shield effect is reduced. But the main problem here is that the main trade off here, we want to reduce the wind flow or protect from the wind. At the same time it will enhance the moisture built up, which will reduce the comfort. Okay. Moderate permeability, so 5 to 40 CFM, balance wind protection and breathability. So, that we should not have very low wind protection, very low permeability, we should have moderate air permeability, and if the air permeability is high, then maximum breathability will achieve, but it will reduce the wind protection, particularly in it will lose the convective heat loss at the high air flow rate in windy condition. Now, in moisture management system, in moisture management main goal is that to move the perspiration away from the body and to keep ourselves thermally comfort, right? And it at the same time it prevent the heat loss through evaporation. Okay. Evaporation should not be there. Now, here you can see perspiration away from the body, prevent heat loss through the evaporation. Now, you can see here, now in case of the moisture in vapor form, so diffusion takes place. Diffusion means where the moisture vapor pressure, it is a high air pressure, here it is a low air pressure. Due to the pressure difference, vapor pressure difference, the moisture gets diffused through the pores, and only in the porous medium the moisture get transmitted, and convective moisture flow is that through the pores the movement of air is that will take away the moisture through the air flow. Okay. Now, you can see the moisture transport mechanism, that wicking is one mechanism, it is for liquid moisture. So, this is the wicking mechanism when in case of sweat, the liquid moisture due to the capillary action, the liquid moisture moves through the fiber structure. Absorption, again basically it should be within the fiber structure, in between the pores, moisture uptake into the fiber structure. So, that is there, and absorption is a process where the moisture vapor can also getting into the fiber structure. Absorption can take place in two ways, one is for liquid moisture, another is for vapor. So, for vapor transmission, particularly for hydrophilic fiber like cotton, viscose, the absorption desorption technique principle mechanism actually works there for in case of moisture vapor transmission, and diffusion we have already discussed, and evaporation. Evaporation is a it is a phase change. So, from liquid phase to vapor phase, when it goes, it takes away from the heat, additional heat from our body. So, that we in the extreme cold climate clothing we should prevent this the evaporative heat loss, but diffusion should be there to actually release our body vapor, moisture vapor which is accumulated inside the microclimate. So, moisture transport in wicking condition, that is a liquid moisture transmission, the wicking takes place by capillary driven force. So, that through the capillary force it is actually the liquid moisture gets transmitted, and capillary network is basically intra and interfiber capillary networks. So, enable direct sweat migration from the skin to outer layer. So, intrafiber and interfiber capillary is the increases the evaporative cooling and thermophysiological comfort. So, for extreme heat condition, evaporative cooling is very important, but in extreme cold condition normally sweating situation does not appear. So, in that case wicking is hardly effect, but moisture vapor transmission is always there. Is this Lucas Washburn equation? This is the Lucas Washburn equation, where L is the liquid penetration distance. So, this type of phenomena does not normally very common in case of extreme cold protective clothing. Absorption of moisture into the fiber structure. So, absorption and desorption type of mechanism is very well there for hydrophilic type fiber. So, fiber gets penetrated into the moisture vapor gets penetrated into the fiber structure by absorption, and when the vapor pressure increases and this vapor will be pushed to the other side. So, moisture absorbs involve physicochemical uptake of the water molecule into the fiber interior, Okay. This is the moisture regain equation. So, W weight means weight of the material, W dry weight of the dry material. So, from there moisture regain we can calculate, and sorption isotherm represent the equilibrium moisture content as a function of relative humidity. So, this is the GAB equation. Now, absorption, moisture uptake into the fiber structure. So, this is basically there are two types of process. One is the fixed second law, where with the time the rate we can calculate. M is the moisture concentration, D is the diffusivity, X is the spatial position of the fiber within the position within the fiber, and diffusion, as we have discussed, it is a basically through the moisture vapor pressure. So, vapor phase moisture transport occurs through the pore network and inter yarn voids. So, there is a two types of these are the yarns. So, inter yarn voids are there, and within the yarn this type of the porous structures are there. So, in those cases where the fiber is not absorbing, the within the pore. So, due to the high pressure, high concentration moisture vapor, due to the pressure difference, it penetrates within the structure, and where it builds up the moisture vapor pressure within the structure, and then it will drive to the other side of the other surface of the fabric, and it the moisture vapor gets diffused to the other side from the our skin. And the fixed second law, it describes, this is the moisture movement, and as per the fixed first law, in a steady state flow, where this is the diffusion coefficient, and now we will be discussing the wind chilled effect. So, moving air increases the convective heat loss, dramatically reduces the effective temperature. That is very important. Effective air temperature and the perceived air temperature is much less than the actual air temperature. Now, let us see the wind resistance design feature. Tight whip construction. So, to protect ourselves from the wind chilled, so what we have to create a weave structure which is tight thread density, okay, ends per inch and peaks per inch. So, fabric set should be tight, particularly we can create with the plain woven structure, because if we have satin and it will be that we cannot create that much tight structure. So, high thread count prevents air penetration. So, thread count should be high, that means low inter yarn space. We can also reduce the wind chilled, which is very commonly used by laminated membranes. So, continuous barrier blocks wind, which allows the water vapor. So, that type of membrane we can use, which will allow the water vapor to transmit through the by maybe the diffusion mechanism, but it will not allow the wind to be penetrated, and coated fabric. So, surface treatment creates wind barrier. So, coated fabrics can be used, and dense fabric, dense knit structure, okay, compact knit loops minimize the air passage. So, different types, that means compact fabric we can use, we can use laminating membrane, and also we can use coated fabrics. So, these are the different ways we can create the this fabric. Now, see the wind resistance capacity, okay, that is a wind chill calculation, this by this formula, wind chilled index, okay, WCI equal to 10 for this is the basically empirical equation, and where V is the wind speed. So, if we this is the V 10 under root V minus V. Now, if we increase the velocity, that means wind chilled effect will reduce, wind chilled index will reduce, and see you can see that under root V 10, and depending on the temperature, whether it will increase or decrease, that also depend on the speed meter per second. Okay. So, basically if effectively normally if we increase the speed, the wind chill index will increase, okay. And this is the temperature, air temperature. So, with the increase in air temperature, or with the decrease in air temperature, if it decreases, then we can see that if it decreases, then what will happen, this will increase. So, wind chilled index will reduce. So, that way we can see this interpretation. So, critical value of wind is more than 1.8 meter per second. So, in that case significantly increase the heat loss. So, wind speed is we should have this. So, 10 meter per hour wind makes minus 7 feel like 7 degrees Celsius feel like minus 19 degrees Celsius. So, that is the feel like effect, and this all this different types of that moisture heat transmission mechanism we have discussed, and we will stop at this point. In next session we will start with the different types of fibers used for protection. Till then, thank you.